Hi everyone! Nice to see all of you back with us. I hope you are all doing well today. Hello! Thank you for joining us again. Hope everyone is doing well, keeping safe. Hello, hello. Okay, so today we have back with us Dr. Po Kang Kai, who will be sharing more on space weather and with specifically with regards to radiation belts, which you would know is kind of one of the part of the challenge statement for this year's International Space Challenge, especially for the open category participants. Of course, if you are a starter category participant, this is a great learning experience for you as well to find out more about space weather and the effects of it. But yeah, so likewise, if you have any questions at any point during the Gang Kai sharing, please feel free to put it into the Q&A box. I would urge you to put it in the Q&A box because the last time we did get a lot of questions, and if you put it into chat, we might not be able to get to it. But yeah, so do try to put it in the Q&A box. Questions. Of course, feel free to use chat to interact with each other. And I know this question is going to come up later. We are recording the current webinar and we will share the video recording with all of you after the webinar. I know we still owe all of you the webinar video recording from last week, but sorry about that. We were a bit backlogged, but you will actually receive the link to both webinars sooner. Hopefully sooner rather than later, along with Gang Kai's slides from last week as well. Gang Kai was very kind to share a couple of resources that we will be sharing with all of you via email. Yeah, so with that said, I won't spend too much time because I want to let Gang Kai get through as much as possible today. But yeah, I'll hand it over to you, Gang Kai.
Hi, everyone. Thank you so much for coming today. Let me share my screen first. Okay. Can you guys see my screen right now?
Yeah, we can see it.
Yes. Okay. Perfect. Okay. So hi, everyone. Thank you so much for coming today. Today, I'm going to talk a little bit about radiation belt physics. It's pretty much an introduction to radiation belt physics. And so it's more also like I will try to relate it back to some of the space weather stuff that I was, some of space weather information that I was that I was sharing last week. Okay, so so what exactly is a radiation belt, right? So by definition, so the radiation belt is a torus-shaped region, okay, between 1.5 to 10 Earth radius around Earth, okay, and it's a area with, of course, as the name suggests, is a region with intense radiation in it, and that is also because the radiation is caused by high energy protons and electrons that is trapped inside the Earth's magnetic field. Okay, so as you can see here, for the you can see from this picture here, you can see that the electron, especially the electron belts, okay, the electron radiation belts, it consists of two different regions, which I will go into the different regions a little bit later. But you can see that there's two regions here, what we call by the inner belt and also the outer belt. Okay, so the inner belt, of course, is very close. It's about 1.5 Earth radius from the center of the Earth, of course. Usually so most of the time it's the LEO, the low Earth orbit, is actually situated within this inner belt, and then you have a slot region. We call it a slot region in between the first and the second radiation belt, and then you have, of course, the outer radiation belt where the geo orbit is located. So it's outside of this radiation belt, and you can see that because of our knowledge of this radiation belt, that we can actually design orbits for satellites that will avoid regions of all this radiation belt, because as I will share with you a little bit later, that all these radiation belts, you really want to avoid staying in those regions for too long. Okay, so a brief history. Okay, so the discovery of the radiation belt is by Professor James Bear Allen from Iowa. And it's really, we consider him to be really like the father of space physics, quite frankly speaking, because because he was really the one who was credited for discovering the radiation belt, and it's from this rocket called the Explorer 1. Okay, and you can see from this very old picture right here, where Professor James Van Allen is the guy in the middle holding up the Explorer 1 satellite, right? So what he did was that he built a Geiger counter instrument, which is to measure radiation, and he sent it up to space. And what he saw from his result, which you can see from this graph on your right hand side here, you can see that as the rocket flies up into space, right? It sees an increase in radiation, which is what we expect, okay? Because we know that back in the days, people know that outside of space, in space, outside of Earth atmosphere, we will have radiation, right? But then what they did not expect was this sudden, as if you can see my cursor, this sudden increase, sudden drop, 0 to 0 count, right? For the radiation between around 20 minutes to 35 minutes, and then it increased back up again. And people don't understand, people thought that maybe the instrument was damaged or something like that, but Professor Van Allen was the one who really kind of like said that no, this is probably not because the instrument failed, but because the instrument saturates, because it's such a high intense radiation that the instrument just cannot measure anymore. So this is what we mean by saturations, right? It went over the limit to how much the instrument can measure. Okay, so then that's when that's when he realized that, oh, there is a radiation belt. There's a region of intense radiation. They haven't called it the radiation belt like then, but it was a region of intense radiation around Earth. Okay, and interestingly, which I'm going to talk about later, is that at the same time, around the same time, people also realized that there is actually a radiation belt around Jupiter. All right, so it's also about the same time. So the Jupiter's radiation belt and the Earth radiation belt is actually discovered around the same time, pretty much. Okay, and of course he was named the Person of the Year he was featured in the Times magazine back in 1959. Okay, so now we're going to talk about. So I'm going to give an introduction, right, to radiation belt. So pretty much the recipe of creating a radiation belt, how radiation belts are being formed, right? So in order to understand how radiation belt is formed, we need to understand how particles move in space, right? So we're going to start off with equation of motions around for particles around in the presence of a magnetic field. All right, and then we have to understand the adiabatic invariance of these particles, and then maybe we will have to look at the phase space density distributions for the plasma itself. And let's throw in a even more complicated equation. This is the Fokker-Planck's equation, where it actually kind of like describe the radial diffusion of these particles. Now, and then I'm pretty sure that by the time you reach this stage, and you become like this, and we are even barely touching the surface of all the physics that you need to understand radiation belt physics. Okay, but we are not going to become like this at the end of this presentation. We are going to I'm going to give you a more qualitative description of how the particles move around Earth in order to form the radiation belt. Okay, so this is it's kind of like a hitchhiker guide, to the radiation belt physics. So fact number one, okay, you need a magnetic field to trap particles. Okay, pretty much particles in space follows magnetic field lines, and for Earth, right, you can actually model, you can simplify them as like a dipole magnetic field. So pretty much it's like a magnet where you have a north-south, pole, and you have all these field lines where the particles can be actually can move along the field lines and be trapped within it. Okay, so So using fact number 1, we can now kind of tell which planets out of the 8 planets in the solar system has a radiation belt. Okay, so we know that Earth has one. Okay, Jupiter has one, and it has been observed. Saturn has one also. Uranus and Neptune also, they think that they have one. They have also some initial observation of it from some of the spacecraft that went further out. But I put a shrug emoji because we really still do not understand how those radiation belts for the IC planets are. Okay, now if we go to the terrestrial planets, right, you have Mars. Mars doesn't have global magnetic field, so we do not have a radiation belt, and Venus also doesn't have one. Now Mercury has a global magnetic field, but because the magnetic field is so small and so weak that it's not enough to trap particles in order to form a radiation belt. Okay, now radiation belt is also a good thing for Earth and for other planets, in the sense that it kind of the presence of it means that the magnetic field is actually trapping particles that come from the external source, right? So you have the sun keep on giving out plasma from the solar wind, and all these particles, when they leak into the magnetic field region for a planet, or for Earth in this case, you know, these particles are being trapped within this radiation belt. Okay, so they don't really kind of like, you know, go in further into the atmosphere. Okay, so fact number 2, you need to know that particles gyrate around a magnetic field line, right? So it kind of moves in this kind of circular, periodic circular motion around a magnetic field lines. Okay, and protons and electrons, they gyrate. So this is called a gyration motion, and so they gyrate in opposite direction. Okay, because one is a positive charge and one is a negative charge. Okay. So fact number 3, right? Particles can be trapped between 2 regions of stronger magnetic field. Now this is a process, or this is a phenomenon called magnetic mirroring. So what happened is that you have this kind of so you can see from the illustration on the left-hand side, you have this kind of so the black solid lines are magnetic field lines, all right, and you can have this kind of we call it a magnetic bottle type of configuration, okay, where on the 2 ends where the field lines are closer together, which means that the magnetic field is stronger in those 2 end regions, and in the center where the magnetic field lines are actually further apart, that's the region where there is a weaker magnetic field, okay, right in the center. Now, if you have a particle that starts off in the center, okay, and is moving towards the end, towards a region of stronger magnetic field line, you will experience what we call by a mirror force. Okay, so as it goes towards the region of intense magnetic field lines, you will receive a retarding force that is actually trying to push it back towards the region of weaker magnetic field. Okay, so once they reach the point BM, right, it will actually totally stops, and then it will go back again. And then now when you travel onto the other end, you will see the same mirror force, and it will go back again. So it's pretty much bouncing back and forth, okay, between those 2 regions of a stronger magnetic field intensity. Okay, so this is what we call by magnetic mirroring. And this is also a very effective way to trap particles, because you can see that the particles are not going anywhere. Okay, now under certain conditions, the particles can escape. Okay, and that is what we will I'll talk a little bit more later. But under certain conditions, they can escape, and they can escape out from the bottle and be lost. Okay, from this bottle itself. Now, so then why do we need to know this, right? Now, if you go back to the picture of the Earth, where you can see that in one field lines, right, the particles are gyrating around the magnetic field line happily, and then it suddenly sees an increase in the magnetic field on the 2 ends, and you can see where the diagram has pointed out where the mirror point is. This is the mirror point where the particles feel the retarding force and cause it to go back again. So pretty much what the particle does is that it goes back and forth between the north and south mirror point. Okay, so in a way, these particles are trapped in there. Okay, and of course, there's different ways to kind of like, let the particles gain enough energy to escape out from this trapping region. Okay. And the fact number 4 is actually that particles drift around Earth due to what we know as the gradient curvature drift. And that is because, as the name suggests, it's because that the Earth magnetic field has a gradient, so it means that it changes spatially. All right, and then also there's a curvature to the field line. As you can see, the field lines are not straight. Like what I've shown in the earlier diagram, is actually curved, right? Because it's a dipole field. So, so it will drift, and because the drift equations are actually a function of the charge of the particles. So, for example, ions are positively charged and electrons are negatively charged. They will drift in opposite direction, and that creates So what happens when we have two charges, a positive and a negative charge going in opposite direction, right? We set up a current. Okay, so this particle motion also sets up what we call as a ring current around Earth itself. Okay, so now so using all this knowledge of particle motion around Earth in the presence of a magnetic field, we combine them all together, and this is what we got. Right, we have particles that are bouncing between the two mirror points, right? And then we have particles going around Earth, right? And then we have all these particles gyrating around the magnetic field line, and so it kind of forms. So we add up all the particle motion together, it kind of forms a torus shape, okay, around Earth. And that's what that's how you actually create. That's why the radiation belt is actually almost like a torus looking shape region around Earth. Okay, and so this is the a diagram of what the particle motion will be if you add all of them together. Okay, so so there are 3 different trapped particle regions, and they are all the same. They are all in the same region. Okay, it's just that different names were given to them because of the energies of the particles itself. Okay, so around Earth, we have first we have what we know as the plasma sphere. The plasma sphere is a sphere of plasma, but except that it's actually on the energies of the particles in it are what we call so we call it as a cold plasma. So by cold plasma, we mean particles with energy of a few electron volts, so EV. Right, so electron, for those of you who are not familiar with electron volts is just another unit. It's not an SI unit. It's just another unit to kind of like it's another unit for energy, and there's a very straightforward conversion between electron volt to joules, which is a unit that we commonly use for energy. Okay, it's for joules. Okay, so plasma sphere is a region with very cold plasma. Okay, and next you have the ring current, like I said, because we have the two different positive and negative charge flowing in different direction around the ring, right? So we form a ring current, and these are particles with kilo electron volts. Okay, so it means that electron volts but multiplied by 10 to the power of 3. Okay, so they are about like 1,000 to 9,000 ish type of electron volts of energy. Okay, and these are very these are considered energetic particles, and even with a kilo electron volt particle, electrons or protons, they are traveling at very high speed around Earth, and they can cause a lot of damage, even just with just a kilo electron volt energy. Okay, they can cause damage to they can cause radiation effects for humans, harmful radiation effects for humans. They can cause they can damage spacecraft. With a kilo electron volt electrons, for example, they can actually cause enough damage to spacecraft. Okay, or those two satellites. All right, and they are able to penetrate very thin armor. And enter, for example, if the ISS has thin enough shielding, a kilo electron volt might be able to enter to go through the shielding and enter into to penetrate into the ISS, for example. All right. So then the next one is the radiation belt, of course, and radiation belts are defined for the name for is reserved for particles that has mega electron volt. So that's 10 to the power of 6 electron volt. Okay, and these particles are very, very fast. Okay. In fact, for electrons, so these are the two belts, like I said just now, are for the electron radiation belts, and these particles are moving at such a high energy. They are moving at such a high speed, so it's almost close to the speed of light around Earth. Okay. And these are, or we also have to, so we also say that these are relativistic electrons because they are traveling at very high speed. Okay, so mega electron volt is definitely like the electrons that you wish you will not that wish that any spacecraft will not encounter, because these are the ones that is going to cause serious damage to your satellite, and let alone if you have humans or humans out there for a prolonged period of time, it's going to cause very harmful radiation effects. Okay. So next is the radiation belt structure. So of course we have, like I said, we have the inner belt is located around like 1.5 to 2 Earth radius. So if you guys recall, the Earth is about 6,500 kilometers, right? So at 1.5 Earth radius, this is about 9,000-ish kilometers to about 12,000 kilometers above from the surface, from the center of the Earth. Okay, so this is about like 3,000 to 6,000 kilometers above the Earth's surface. All right, and it contains mostly electrons, protons, and ions, and it's very stable. Okay, it's fairly stable. All right, and we know that it doesn't really change as much. Now the outer belt is the one that is most dynamic, and it's actually ignore the there's typo error. So it's not 1.5 to 2 Earth radius, it's actually further out. Okay, and it can extend all the way from to 10 Earth radius. And it contains mostly of relativistic electrons with energies that can go up to 10 mega electron volt. That is 10 to the power 7 electron volts. Okay, and it's very dynamic because it's the outermost belt, and any changes to your magnetic field, to the Earth's magnetic field, okay, or to the Earth's magnetosphere, could actually changes this belt, the location of this belt, the intensity of the radiation. Okay, and also all the particles that is inside it. All right, and so the slot region here is a region where has a lower radiation region. Okay, and so why is there a slot region here? Now, interestingly, so one thing that you also need to know is that particles and waves can interact with each other. So wave in physics contains energy also, and particles, of course, contains energy also. Now, the two of them can actually exchange energy when they interact, okay? Or in a way, we call it when they are in resonance, they can actually exchange energy easily. So now what happened is that there is a type of plasma waves called the Whistler waves, okay? That, as the name suggests, if you hear it on the radio, you'll hear it like a whistling sound. So this Whistler's wave actually can interact with the electrons, and it interacts in the electrons in the region that maps around the region where the slot region is being observed. They interact with all these electrons. Okay, they give electrons a lot of energy. Okay, and so they kind of like kick it out of the trap region, and so now all these electrons are precipitating onto either to their loss. Okay, and they precipitate into the Earth atmosphere. So, and that's the reason why not a lot of electrons are being trapped in the slot region. So that's why we do not observe. Intense radiation in the slot regions. Okay. All right. So interaction with waves, with plasma waves, in space can actually lead to particle loss. And like what I was saying, particles are trapped in the magnetic bottle. This is one of the ways to actually kick them out of that trapping region. Okay. So just how dangerous are radiation belts, right? I've been talking about radiation belts. They are very dangerous. You really wouldn't want to send your spacecraft there, let alone be there physically, right? So how dangerous are they? So for a KeV or a MeV energy particles, first thing, it can cause surface charging on the satellite. Okay, so what happens is that when the particles encounter a surface, it can give it a charge, right? It can give it a positive or negative charge, depending on whether it's a positive or it's an electron or a proton that hits it, right? Now, because the surface of the spacecraft or a satellite is not even, right? So there will be regions that are more negatively charged or positively charged, okay? And so because you have an imbalance in charge, it can cause what we know as a arc discharge. And having this arc discharge can actually damage electronics, and it can actually also degrade surface properties. Like you can see from this diagram here, where the surface is actually damaged, is burnt out, caused by a electrostatic discharge arcing. Okay. Now, of course, when you are in the radiation belt, you receive what we call you will experience what we call the total dose effect, right? So the displacement damage is when the particles but the particles was able to penetrate the surface material, and it causes the properties of the material to actually change, and that could actually degrade, for example, the solar panels materials, any materials is surrounding the satellite, and also inside the satellite, where you have all the microelectronics, the delicate microelectronics that is running the satellites itself. Okay, and also all these, so the total dose effect. Now, this is kind of thing that if you receive the radiation for a short period of time, it's not going to cause as much damage. But if you are constantly in the radiation belt itself, over time, you're going to receive a lot of, it's a sum of the radiation that you receive. So this is what we mean by total dose effect. All right. And we have the ionizing radiation. Of course, as a human, you wouldn't want to be inside the radiation belt, because it could actually cause harmful radiation effects to you. All right. And there's another thing called the single event upsets, where it can actually cause the corrupted data. It can cause the data to be corrupted and systems shut down. So what happened was that for MEV electrons, for example, it's able to penetrate a lot. It is able to penetrate materials, thick enough materials, and once it penetrates it, these particles, these electrons, can actually hit the electronics, and it can cause like a flip in your. So we know that data is being data is being transmitted by binaries like 1, 0, and all these are the way that data are being transmitted. Now the electrons can actually flip one of these bits, and just by changing one bit, it could cause the systems on board the satellites to actually think that it's doing something else, that you're giving it some other commands, and it can do something weird. It can either cause a shutdown, it can either cause it to go into a safe mode, or it can even go into like some sort of like a weird orbit motion that you did not intend it to do. Okay, so for example, we were talking we were discussing earlier on that there's this Malaysian satellite, right? That actually for some weird reason went into like weird configuration, and it's not in the right how do I say this? It's kind of like it's it's kind of not looking in the right direction as they want it to be, right? It's a telecommunication satellite, right? And the engineers couldn't figure out, what's wrong. And we were discussing that maybe it's because of, they think that it might be a space weather event, and most likely it could be one of these single event upsets where, electrons can enter in, high energy electrons can enter into the spacecraft, penetrate the spacecraft, and cause like, the code or the program to be corrupted, and the spacecraft go into some sort of like a weird configuration, and then once it goes into that, it's very hard for the spacecraft to actually, or the satellites to actually come back from it. Okay, so you have to do recess and things like that, but sometimes it might not be as easy as that. And so that satellite is pretty much, it could be actually, it could be gone forever. You might not be able to recover from that. So single events upsets can cause actually, in certain cases, can cause the satellite to just be pretty much useless and deorbit, and or like go into some sort of a graveyard orbit where it's not going to work, but it still continue orbiting around Earth, for example. Okay. So of course, and then we have the radiation hazards for astronauts on the ISS. Now, the ISS actually is orbiting around within the inside of the inner belt. Okay, but there are some times where the ISS can actually schemes on the lower latitude footprints. Okay, of the radiation belt. And this is really because that, so one thing that you need to know is that the Earth rotates, so the Earth rotational axis is very different from the Earth's dipole magnetic field axis. Okay, so the dipole is actually tilted at a certain angle away from the rotational axis. So in a way, the ISS could actually, there are certain times where ISS can come very close to the radiation belt. Okay, and with that, when it has that, when they encounter the radiation belt, or get close enough to it, the astronauts cannot go out of the ISS. They cannot do spacewalk and things like that. They have to hide inside the ISS until it's safe for them to go out. Okay. So these are just some of the harmful effects of what a KEV or MEV, high energy particles, can do to electronics, to materials, to humans itself. And some of these, I mean, it can cause a serious health effect for humans, of course, but also it can cause a lot of financial damages, okay, to companies, for example, having telecommunication satellites, right? And when all these satellites fail, that's where they have to replace it, and they have to there's a lot of other problems that come with it. So it's something that they would love to avoid if possible, right? And so some of the unanswered questions, right, that we still have, and there's a lot of things that we still do not know about the radiation belt, even though it's the first region to be discovered. Okay, so the Van Allen radiation belt is very highly dynamic. Now, that's something that we know, but how dynamic, how it changes, that's something that we do not know. We not yet know. Okay, so one of the things is that how does the space weather affects the temporal and spatial variability of the radiation belts itself, right? So under quiet conditions, right, where there's no extreme space weather, a good time, for example, right, we know that the radiation belt is fairly stable. Okay, we know where it is. But when there is a space weather event, for example, that's where the radiation belt will change. Okay, mostly on the outer belt, but we are also looking at the inner belt and how it changed with time and in space, in spatial location. Okay, so for example, during a extreme weather event, it can compress the entire magnetosphere smaller, right? And so that means that your radiation belt will also be closer to Earth itself. But then also there's also a lot of other processes that can actually cause the particles inside the belts to be lost away. So there's some times that we also see emptying of the radiation belts, the particles in the radiation belts, right? And so how does it change with time and with space? these are all the things that we need to look into. Now, in order to do so, we need more than one spacecraft to actually to understand that, and hence the Van Allen probe, right, is actually 2 spacecraft, okay, at 2 different locations orbiting around, and hence you can actually see how does the radiation belt changes with time, okay, and also we need it to be in different locations to see how it changes in spatial location, right? Now, of course, 2 is also not enough. We really need a constellation of satellites around Earth in order to fully understand the how does the radiation belt changes, okay? But of course, even having 2 is a huge amount of money to be sending, just 2 spacecraft up there to study the radiation belt. But ultimately we do need more, okay? And the other thing is, what is the acceleration, loss, and the source cross mechanism for all these energetic particles in the belts, right? Because we know that the belts doesn't exist there by itself. There has to be some sort of processes to actually inject the particles, the energetic particles, into the belt itself, right? And then there are also other processes that accelerates it, okay, make it gain energy, and also what are the process where it actually lose the particles? How does the particles goes from being trapped within the radiation belt regions to be lost, to escape away from this region, okay? So these are still the processes and mechanisms that we do not fully understand, okay? Even though Van Allen probe has allowed us to actually understand a lot about all the physics of the radiation belt, there is still more there's still more unanswered questions to be answered, to be honest. And there are people who spend their entire career, working with more numerical models and thinking about what are the possible future missions that they could embark on, flight missions to embark on, to actually investigate some of these questions, some of these problems that we still have regarding the radiation belt physics. Okay. So now I'm going to change gear a little bit and talk about planetary radiation belt. Okay, so mainly is the Jupiter's radiation belt, which, like I said earlier, is actually discovered around the same time as the Earth radiation belt, but it's in a slightly different way. All right, so the Earth radiation belt is discovered by sending a rocket, Explorer 1, right, and it was observed in the data from the Explorer 1, and so it's more like an in situ measurement of the radiation belt. But the Jupiter's radiation belt is a little bit different because we will not be able to send a spacecraft. A spacecraft will not get to Jupiter, right, until decades later. Okay, so the Earth radiation belt is discovered in 1958, but we will have to wait for a few decades before we have the technology to send a spacecraft all the way to Jupiter, which is at 5 astronomical units away. Now, so then how do we observe the radiation belt? Now, it turns out that Jupiter's radiation belt is so strong, so intense, that the particles are traveling at such a high speed that they are able to actually emit something we call as it is able to emit radiation on itself from the belt, and as a form of a radio wave, and the astronomers at Earth is able to hear all these radio emissions from Jupiter. Okay, and from that, so the Jupiter itself is emitting all these radio waves, and when they hear it, the astronomers in the beginning, they are not able to figure out, why is Jupiter giving out such strong radio waves, and then slowly they realize that it's actually from the radiation belt itself. Okay. And so what makes Jupiter's radiation belt so strong, so intense, is because Jupiter really has the largest and the strongest magnetic field in the entire solar system. Okay, so the thing that I always like to share with people, a fun fact, is that, for example, if you are somehow able to light up the entire magnetic field, okay, or magnetosphere of Jupiter itself, if you light it up from the surface of the Earth and you look at it, it will be bigger than how we are looking. The size, it will be bigger than the size of the moon. from the surface of the Earth, and this is how big Jupiter's Jupiter's magnetosphere is, or the magnetic field is. Okay, so the electron flux, or the the electron intensity at Jupiter is about 10,000 times greater than Earth. Okay, so it's very strong, very intense. And not to mention that, so unlike Earth, where Earth, we only have a moon, and the moon is pretty much not doing anything, just orbiting around Earth. For Jupiter, it's different. Jupiter has a moon, Io, that actually is the most volcanic moon in the solar system. It's constantly spewing out all these materials out, okay, into the Jupiter's plasma environment, okay, and all these. So this is like a source, where once it spews out, you can end up in the Jupiter's radiation belt region, right? So it's like a source to kind of supply the radiation belt with particles, okay, and it's also and together with like efficient acceleration mechanism, right? So it supplies the Jupiter's radiation inner magnetosphere, or the radiation belt region, with enormous energy. Okay, so that's why we have the most intense radiation belt in the solar system, in the Jovian system. Okay, so you can see here that so we have made observation of Jupiter's radiation belt regions. All right. So of course, then learning from that, this will be a good place for us to learn radiation belt, and so and of course we want to learn more about the planet itself, right? And so we had to send spacecraft there. But one of the biggest thing that the spacecraft had, the biggest problem that the spacecraft had to overcome is this intense radiation, right? And it's something that is not a big issue for other planets, but for Jupiter it is a very big issue. And so scientists, when they send a spacecraft, for example, in here we have the Juno spacecraft, right? And so they had to think of a creative way on how to make sure that the spacecraft can survive the intense radiation environment at Jupiter. Okay, so one of the way is to minimize exposure. And how do we minimize exposure, right? Like I said just now, the effects of radiation is really determined on how long you spend, okay, inside the radiation belt. Now, so that's the reason why when we study the radiation belt, we try not to stay too long inside the radiation belt, because the longer you stay inside the radiation belt, the more damaging effect the radiation can cause to your satellite or to your spacecraft itself. So what they do is that they design an orbit to fly through the radiation belt while making measurements inside the radiation belt, but not stay too long inside it. So you're minimizing the exposure of it. Okay, so for Juno case, you can see that this is the Jupiter's radiation belt, and you can see that it takes a highly elliptical orbit where it spends some time inside the radiation belt, enough to make observation, to do the size that you need, and then it exits out and goes into a larger orbit. Okay, and it goes further out from Jupiter, and then it comes back again. And there are also regions where there is of lower radiation intensity, and that's where the closest approach usually take place. Okay, around the pole and sometimes around the region that is very close to the planet itself. Okay. Now the second thing is, of course, increased shielding. Then how do we protect against radiation, right? We just have like increased shielding. Now at Earth, how do we some of those, if you think about those Cold War bunkers, right? They have like tons of lead shielding, right, to shoot off the radiation, okay, the ionizing radiation. Now, of course, for practical purposes, we cannot be flying, thick lead walls in space. So now what they do is that instead of using lead, they use titanium. So for the Juno spacecraft, in order to make sure that the radiation is controlled, what they do is they build titanium boards around the electronics to shield it from radiation. Even the titanium board is not enough to totally shield it, such that the spacecraft can be in constant orbit within the radiation belt region. So that's the reason why they have to also take on a orbit that will minimize the exposure. Okay, so these are some of the mitigation strategies that we can learn from the Juno spacecraft around Jupiter. Okay, so and the wall alone is already 157 kilogram, which is huge and heavy, in spacecraft term. Okay, and all the instruments that is outside, okay, all the equipment that is outside of this titanium vault, right? They of course you cannot put everything in the vault, right? Because the solar panel has to be outside, for example, and we know that the solar panel, the radiation can degrade the solar panel itself, or some other communication equipment to communicate back to Earth, right? All those cannot be inside the shielding itself. So what they do is that they have to actually use material that are resistant to radiation effects. Okay, so the cartoon diagram here which tells you how much radiation the spacecraft received by the end of the mission, and some of these can be very big, like we are going up to like kilorad or mega rad itself, and the materials have to be made to withstand the high the intense radiation that it will see in Jupiter's radiation belt or the radiation environment. Okay, so pretty much this is all I have actually. So this is really just to give you a good overview, introductory to radiation belt physics, and some of the harmful effects of the radiation itself. I believe there will be another speaker to talk about the Van Allen belt in more detail. She's my friend and from Colorado, and she's really an expert in the Van Allen probe and the radiation belt. So and I think she also works in the mission itself. So I think she'll be a good person to give you more information, I guess. But yeah, that's all I have.
Thank you. So now we'll jump into the questions for Dr. Poh. We have quite a few actually. So.
Oh, okay.
Yeah, so the first one we have is, so someone asked, could we assume that the plasma in the outer and inner radiation belt to have a gentle plasma density gradient?
Yes, it will. Well, I'm not sure about the I'm not too sure about the density gradient of it. Yeah, it really has to depend, I guess. By density gradient means that the density changes, I suppose changes with distance away from the planet, right? That I'm not too sure. We have to really look at the data to actually understand that, and I would think that will be suitable. I think Ling Ying will be able to answer that question better. Yeah, because she has looked at the data from Van Allen probe itself.
So Ling Ying, which is our speaker 2 weeks from now, I believe. I think her talk is scheduled for the 25th of September, if I'm not wrong. So she will be going more into that, specifically the Van Allen belts. It's on Saturday, it's at 11 a.m. But changing the times a bit, I understand. But hopefully you guys can still join us for that one. Yeah, we have a couple of other questions about why certain planets have radiation belts, and also to re-explain how these planets create these radiation belts. So like, I think you ask, why is it that Mars doesn't have a radiation belt specifically?
That's a very good question. So let me go back to this cute diagram that I have. Let me go back to this cute diagram that we have here. Okay, so the radiation belt is created because the particles are trapped, right? And so in order to trap the particles, the electrons and the ions, we really need a magnetic field, right? For the planet, so the planet must generate its own magnetic field. Okay, so the planets that we know has its own magnetic field are, Mercury, Earth, Jupiter, Saturn, Uranus, and Neptune. Okay, because we observe them directly. Now, Mars used to have, the theory is that Mars used to have its own magnetic field, but then over time it is lost. So now Mars doesn't have a global magnetic field, so to say. Okay, so it's without a global magnetic field, particles cannot be tracked. Okay, so Venus also has no magnetic field itself, so it's not unable to track particles. So we could not form a radiation belt. Okay, now there's also so having a magnetic field doesn't really also kind of say that that doesn't assure that the planet has a radiation belt. For example, like Mercury. Okay, Mercury has a weak magnetic field. Okay, so it's so weak and so small that it's unable to trap any particles in there. So we also do not observe radiation belt in Mercury. Now, only at Earth, Jupiter, and Saturn, and Uranus and Neptune, these 5 planets are able to have a radiation belt because they have the magnetic field and they have strong enough magnetic field to actually trap the particles. Now, there are a lot of theories. Right now, there's a lot of people are trying to find out, people still really do not understand, where are the particles coming from? Okay, so a lot of people think that well, in so there are internal source of particles. There's also external source of particles. So by external source, we mean by certain processes that actually can actually inject particles from further away from Earth, into the inner region, okay, the inner magnetosphere region, which we define as the radiation belt region. So all these so during, for example, during space weather events, I will not go into much detail, but during space weather events, particles can actually leak into the magnetosphere for Earth, for example, right? And then through a process called reconnection, magnetic reconnection, further away from Earth, in the night side of Earth, you can actually inject particles into the inner magnetosphere or into the radiation belt region. So that's what we think as external source of particles. So and that's happening in most of the what we call the magnetized planets. So planets with a magnetic field itself. So really, you need a magnetic field to really have a radiation, a strong enough magnetic field around the planet to have a radiation belt.
And guys, you don't need to feel bad for Pluto. I see some of the comments.
Yeah, it's really not in the. But Pluto is not magnetized either, so we don't have a radiation belt. But yes, yeah. Pluto. I'm sorry. I mean, yeah, I know.
It's not an official planet. It's a dwarf planet. I think it counts as a dwarf planet still.
Yeah, that's true. It's so funny because the older version of this kind of lineup of the planets, they still have Pluto actually, and Pluto looks very very sad. So I don't know. Maybe it's sad because it's being left out right now. But yes. Yeah. Unfortunately, yeah. But Pluto is a dwarf planet, and usually dwarf planets doesn't have a magnetic field on its own. So yeah.
The victim of downsizing, yes.
Yeah,
unfortunately,
I know.
Yeah. So unfortunately, Pluto not officially a planet, but it is considered a dwarf planet.
It is considered, yes.
Yeah.
One other thing. Sorry, if you don't mind me, there's one other thing that I want to point out also.
Oh yeah, sure.
Sorry, something very interesting, which I just thought about it. So Neptune and Uranus, the IC planets, is a little bit different. So because of the orientation of their magnetic field, their radiation belt region will also be very different. So as you know, I think I can't remember from my astronomy 101 class. Either one of the planet has, or actually both has very odd. So the tilt of the magnetic field, the dipole is actually very much away from its rotational axis. So its whole magnetosphere is kind of like toppled over, and that can actually create a very weird structure of the radiation belt also. But we will need a spacecraft out there to really study it before we can say for sure how does the radiation belt is going to look like for the IC planets. But for now, we know that I think it's not going to look anything like the Earth.
So we do have a couple more questions with regards to like planets. So I thought I'd just jump to those first since we're on this topic. So Pranav asks, how can Mars have auroras without a magnetic field?
Yes. So Mars is a very special case. That's a very good question. Actually, you guys are asking questions that that I am teaching in a college or graduate or PhD, teaching to a PhD student actually, or a senior in undergraduate class. But that's a very good question. Okay, great. So Mars has aurora, yes, and it's a very different type of aurora, right? So Mars has aurora is actually emitting, unlike Earth, is actually emitting at a different wavelength of the light spectrum. So it's not on the visible light spectrum. Now, Mars aurora is also caused by I believe is caused by the interaction of the particles with its own atmosphere. Okay. Now, the one thing that is different and is that Mars has a very weird thing. So, like I said, Mars used to have a magnetic field, okay, but it lost its magnetic field. But what happened is that the surface of Mars, okay, the crustal region of Mars still has some so-called trapped remnants of the magnetic field from its ancient magnetic field. Okay, so Mars is what we call by a hybrid magnetosphere. It doesn't have a global magnetic field, but it has what we know as a crustal magnetic field. So there are some regions at Mars where it has very strong magnetic field. When we observe that, we measure that, okay, and it reacts differently than, for example, Venus, where Venus totally has no crustal magnetic field or whatsoever. Okay, now crustal magnetic field only occurs in certain planets where there is very little or no volcanic activity at all. Okay, so Venus has so much volcanic activity that the crust, if you learn from your from our geography, right, we always know about, like, for Earth, right, the plates subducts, and then it becomes the magma or something, and then it constantly, then you have volcanoes spewing out new materials out into the surface. Now those kind of activity, the tectonic activity at Venus is so much activity there that that they cannot have a remnant or random crustal magnetic field. But Mars has very little tectonic activity. So that's why it's the crust of Mars is able to be able to still have leftover, so-called leftover magnetic field from Mars. From its ancient magnetic field. So this is actually we know right now. But that's a good question, by the way. That's a very good question. So it has a hybrid. It's in between Venus and Earth, for example. We don't really call it we don't really call it a non-magnetized planet either.
So I think on that, so this is like all these questions are coming in very conveniently. Saina asked, due to what reasons did Mars lose its magnetic field then? Like, what caused it to weaken? Was it like due to the weakening of poles or any other specific reasons that could cause this?
That's a very good question. If you know the answer to that question, let me know, because it's really still an active area of research. People does research on this, and we are sending, for example, we are sending like the rovers. We are sending spacecraft to Mars to really actually try to understand what happened. This is one of the major science questions that NASA spent so much money on, to really figure out what happened to Mars magnetic field. We do not. There are models to try to extrapolate all the way back in time to really see it. We think that maybe the core just stopped working. So in order to have a magnetic field, right, the core is caused by dynamo. We think that it's caused by dynamo effect inside the core, and or inside the interior of the planet itself. So maybe something went wrong, and the switch was turned off, and it stopped working then. And but we really do not know, and so that's why we send so much mission to Mars to really just to figure it out. It used to be that Mars mission is, follow the water trail, right? Try to look for water, but but there's also a huge component that is that not many people know, is really to figure out what is the history of Mars itself. Actually, the lack of water at Mars is related to the lack of magnetic field at Mars also. So they are kind of interrelated. Because think about this way, we always talk about the magnetic field protecting Earth, right, from the solar wind. Okay, now without the magnetic field at Mars, the solar wind just strip away at Mars atmosphere and strip all the the water that comes with it and things like that. So that's why Mars has a very thin atmosphere, and we also think that that is also the reason why the Mars becomes it is where there's not a lot of surface water on it. Just something to add also is that the remnant, the crustal magnetic field that I was talking about at Mars, that is actually there were people that's trying to study, like how maybe that humans actually on Mars should actually stay around the regions where there is strong magnetic field, because it can actually protects the astronauts better against radiation. Or even like particles from the solar wind itself. So those are the things that people are thinking about.
I mean, I think even on Earth, we've been discussing things like, or there's been theories about like the Earth's magnetism, like the poles flipping, or like crazy, like things like that. That's a bit also kind of unexplained, that we cannot really understand at the moment. Yeah, if anyone has like any way of like figuring the answer out to that, you can always let us know. I mean, technically, every student here has a chance of figuring, like becoming
there is
to figure out these answers, right? Because space is constantly like evolving so fast.
Yes, and to be honest, space missions take years, decades, and
True.
Yeah, and you guys are you guys as the next generation are really the people to actually will be able to answer some of these questions, to be honest. And there's a lot of exciting things that is going to happen in space, especially science discovery wise. It's going to happen in the next couple of decades. So yeah.
Okay, we still have a lot of questions to go through.
Go ahead. Yeah, sure.
We got a bit distracted there. Sorry, guys.
Yes.
Yeah. So what's the typical energy of gamma rays and X-rays emitted by a solar flare, M or X scale outside low Earth orbit? Also, it would be really helpful if you could recommend some radiation shielding materials being utilized currently by satellites and rovers outside of Earth's magnetic field.
Okay, so that's a very good question. So the usually we are talking about, so for the first part of the question, right? Usually we're talking about for all these energetic particles, we're talking about kilo electron volt, okay, or mega electron volt. I think there are some instances where I heard giga electron volt, which is like the next order of magnitude up. So that's GeV, not MeV, but GeV, which is even much more intense. Okay. So that's the energy range that we are talking about. But quite frankly speaking, when people start to talk about MeV, all those radiation are destructive enough that so when you have GeV radiation, that's going to even be be worse, right? So it really depends on what is the energy level of these particles that's coming in that we are observing, that actually will determine how much shielding we need, how much how are we going to mitigate that kind of a level of radiation, mitigate the effects of that kind of level of radiation. Now, regarding the materials and things like that, unfortunately, I'm not a expert on that, so I can't really answer that question. I would leave it to someone who actually has a better understanding of material, or the different material, the properties of the materials, to actually answer that question. But I mean from what I learned from physics, right? Radiations, we can use lead, I guess. and also I talk about a little bit about the titanium volt that is being used for the Juno spacecraft at Jupiter. So I guess that's another material that can be used also.
We do have a couple of satellite engineer experts on our judging panel or like our grading panel. So probably we can forward these kind of questions about materials to them, and then we'll just drop me an email about the questions that you have, maybe with regard to that maybe we couldn't answer in this session, and then we can forward it to the relevant expert and then get back to you on it. But yeah. So Sumit asks, can we say that radiation pressure is the highest in radiation belt region, in the radiation belt region?
The radiation pressure. Now, okay, this is a very good question. So radiation pressure is a little bit different than the radiation belt radiation. So my understanding of radiation pressure is usually we were taught in class when I was in school, right? That's the only time that I heard about radiation pressure is when they were trying to harness the pressure caused by the photons that is being emitted from the sun and acts like a pressure to kind of like push. It exerts a kind of pressure. So they were trying to work on like some sort of like a different propulsion system. Mainly they call it the solar sail, I think. So pretty much like, just like how a ship move across the sea, back in the days when you have like the winds blowing and then they have a big sail. So what they have is that the certain spacecraft, they will deploy like a very big sail, a solar sail. And just by harnessing the radiation pressure from the sun, that they are able to, move across and make that interplanetary travel. So they are just a little bit. I believe they are a little bit different than the radiation in the radiation belt.
Kaiwen asks, why are the radiation belts at these specific altitudes? Is it because the solar wind is usually deflected at these altitudes that causes them to form around this?
That's a very good question, actually. So the solar winds are deflected actually further out. The solar winds are deflected at around 15 to 20 Earth radius. Okay, so they are really further out. Sometimes during intense solar storm, for example, or like a space weather event, it can actually push the deflection point for the solar wind to be actually closer and inside within to be nearer at 10 Earth radius, so to be closer. Right, but these radiation belts are actually so there are the equations that I showed you earlier on. Okay, that I showed you earlier on. Those are the equations that determines how the particles are being tracked. Now the particles are being tracked at that region. So the radiation belt forms at that region is because of the energies and the how do I say this? It's because of the magnetic field at that region, where at that particular strength, at that particular magnetic field strength, that the particles can get trapped within that region. Anything happen outside of it is subjected to that very dynamic changes, and that the particles are harder to track. So there's a set of equations that actually can help you determine, or can allow you to determine and calculate, where are the radiation belts being formed. So so without going to the equations is it's a little bit hard to kind of like say that why the radiation belts are formed but I guess it's got to do with the drift path, the trajectory and the path of the particles that is actually drifting around and within the magnetosphere itself.
I'm going to try to merge some of the questions together so that we can go through them a little faster. So someone asked if you could re-explain what single event upsets are, and if SEU can affect quantum computing. So this is a question from Arshad.
Oh. Now, that's a very good question. Okay, so my understanding of a SEU event is that particles, radiation coming in, and it actually affects the electronics and how data is being transmitted within the electronics itself. and as far as I know, corrupt the data in that sense, and it can go into like different type of modes. It can actually tell the spacecraft to do something that is not supposed to be doing, or it can actually cause so that I believe that there are some fail-safe programs inside a satellite that actually tells it that if something wrong happens, right, it will automatically shut down or go into a safe mode and try to protect itself. As far as I know, that's what I know from some experience for like space missions and things like that. And the radiation can actually cause this kind of event where the information is corrupted and is bad, and it makes the spacecraft go into some sort of safe mode or shut it down. Sorry, what was the second part of the question again?
Which is,
can
SEUs affect quantum computing?
Quantum computing. Now, I'm not. So I'm not actually an expert in quantum. Actually, I do not know really much about quantum computing.
To be fair, not a lot of people know much about quantum. Quantum is a very
quantum is one thing
topic.
That just by mentioning the word quantum, it triggers a lot of nightmares. But if I were to make a guess, it could actually it is most likely to actually it could actually affect the ability for the onboard systems to actually to do some sort of quantum computing and things like that, because quantum is still pretty much electrons and particles, right? Electrons, protons, and things like that. So and all these radiations are electrons and protons itself, and they probably can interact, and they can cause a lot of issues that the engineers really hope to avoid on the spaceship. But I will let the experts answer that. We're actually experts in quantum computing to say more about that.
Experts in quantum computing. That's a difficult.
I know.
That's a difficult topic. I feel like not many people will consider themselves experts in quantum in any way. But yeah. I mean, maybe one of you could become an expert in quantum computing, and you can let us know. So
in space, I think they're all right, isn't it?
Yeah. So I think they're trying to develop a quantum computer for the satellite that is supposed to replace the Hubble. I think they wanted to replace it with they want to insert a quantum computer in that. I'm not sure what the status on that was, but yeah.
The thing is that the more sophisticated, sometimes, so in my experience, right, the things that people send to space, let me tell you this, the things that NASA sent to space, they are technologies that are decades old, because those technologies that are so old, like even before I was born actually, and the reason why that is that because they are very reliable. They are almost kind of like not so digital, but analog enough in a sense. so I mean, they are digital anyway. Sorry, they are still digital, but the technology is so far back but they have proven, they have a good flight history, and proven flight history of being able to survive in space. Sometimes newer technologies, the thing is that the newer technology, the more susceptible it is to radiation effects. And for example, like we were discussing, right, earlier on, like how if there's a space weather events, most of these CubeSats won't be able to survive the radiation. I mean, CubeSats are mainly around within the inner belt region, right? So I mean, we would love to, like I was saying just now, we would love to have multiple spacecraft, like hundreds of surrounding Earth, so that we can study the radiation belt, right? But in order to do that, people actually has been suggesting, why not just launch CubeSats, right? But the problem is that CubeSats are small, and the moment they enter, there's no guarantee that they will not shut down or they will not be killed once they go into the radiation belt region, right? But then, okay, then we increase the shielding. But if you increase the shielding, it's not called a CubeSat anymore because then you exceed the weight limit for the CubeSats, right? So so there's always this so of course then the thing is to really build hardware that is really resistant to radiation, and make it smaller. So that's something that they're actually trying to figure out. I guess the technology really hasn't caught up, or maybe I'm wrong. So
I mean, it's a good point for all the people here to note, right? Because I mean, our challenge to you is to design a satellite mission to study space weather. So if you are planning to go with CubeSats, just know that the smaller you go, the more fragile it's likely to be. And then of course, then you have to figure out ways to make it more, more able to endure all these like solar flares and all these things. So these are kind of the questions that you guys have to ask when you're working on your projects. And just as a fact, like we were just talking about this before, was that it's not even like CubeSats that are at risk, that like big comm satellites, telecommunication satellites also have a chance of getting affected by all this solar flares and space weather. But yeah. Okay, I think we had a question from Angeline, which might be this one. I'm not sure because it's submitted as anonymous. Is that regarding the slowing down of ions, is it in some ways related to Lenz's law, like the slowing down of a magnet falling through a metal pipe? This one's Lenz's law.
So by slowing down of electrons,
is regarding the slowing down of ions. I think it was regarding fact 2 or 3. I think 3 maybe.
Yes. Okay.
Yeah.
So it's not. So the answer to that, why it slows down, okay, is that when you have a gyrating particles, when you have particles, for example, when you have an electron or a proton gyrating around a magnetic field, it creates a current loop, right? When you have so the more physical or the more mathematical aspect of this is that you form when you have a particle gyrating around a magnetic field, it causes a current loop, right? When you have a current loop, now then you can use the equation F equals to mu, which is the magnetic moment caused by this current, multiplied by the magnetic field. And the equation will tell you that it's actually acting in the opposite direction of it's actually acting along the magnetic field line, and it's actually acting in the direction towards the region where it has a weaker magnetic field. So then in this case, right, if you see my cursor, when you have a particles out somewhere in the middle, right, it will actually push the tries to want to push the net force, right? We always talk about F equals to m. Net force is trying to push the particle back towards the region where there's a weaker magnetic field. So there's kind of like there's a deceleration component to that. So that's the physics behind why particles slow down and as it approach a region where there's a stronger magnetic field. And it's also got to do with these sets of equation where so these sets of equation right here, because the mu, which is the magnetic moment, has to be constant in the adiabatic system. But anyway, but not to go any deeper into that, I literally just gave this lecture last week to a graduate student, to a class of graduate student. But yes, but that's the basics of it. Yeah. But so it can be explained in very simple terms, but you really have to look at the equations to really understand, like, why particles will experience that force. But for example, the student that asked that question, you can send me an email, and I can actually provide you with the resources if you're interested. I can provide you with the resources to actually look at the equations and really explain more in depth on. I can even send you the slides that I gave for my class, and you it's actually interesting, because the way people track the way this is actually a simplest form of course, it's going to be difficult than this, but this is actually a way to track particles. And how they track particles, this is also using they call it magnetic confinement, to actually confine the particles inside a region. And this is it's going to be more difficult than this, but this is also the same underlying principle on how they track particles inside a nuclear reactor in order to gain nuclear fusion. So this is the same thing, because nuclear fusion is also with plasma, and how they try to start fusion, they have to track the particle first. And this is how they do it also. So space physics and nuclear physics is really almost the same thing, to be honest. Physicists have to learn plasma physics either. So
yeah, so guys, just know that you are dealing with questions that graduate students are trying to answer. So if you cannot answer them in your paper or like in your project, it is perfectly fine. We are not expecting like you to be able to solve some of the greatest questions in space, right, and the space industry right now. We're looking for, we're more interested in seeing like how you guys approach these kind of issues, and seeing what kind of ideas you can come up with that could potentially help with the research in this area. But just know that you're dealing with like really difficult questions. So just don't feel disheartened, because everyone is probably has the same questions as you. Scientists have not solved these questions as well. It's just go for it, like just try and go for it. And you never know what you might find out of working on your projects. But speaking of email, we might actually have to compile a couple of these questions into an email and send it over to Dr. Po to answer them, because we still have a lot and we're kind of out of time. But just to kind of wrap up today's session on a bit of a more personal note, I tend to like to end with this kind of questions just because it's a bit I guess it helps our like participants also know what's kind of like opportunities available in the industry and in the field. Someone asked, could you please talk a little bit about what your current research interests are, what we can expect in the near future in terms in this field, and what are some trends or research areas that are maybe worth pursuing for someone who's interested? Yeah.
That's a very, very good question. So all these are information that information. The information that I presented are the ones that I learned in my class many years ago, and then now I'm actually trying to teach them in the class, right? But my research is very different from it's different. It's more specific. This is really the big picture. The space weather lectures that the space weather presentation that I gave last week, and the presentation that I gave about radiation belt physics is more like a bigger picture, really. So a bigger picture. But my actual research is actually very specific. For example, so I work on Earth, but I work mainly in the what we call the magnetotail of the Earth. Right, so when we have a magnetosphere, right, there's a region that is very far away from the planet, from Earth itself, that is actually causing the particles to actually so it's kind of like it's a process where the particles from the solar wind can actually enter into the inner magnetosphere, right? And I'm working on a specific process called magnetic reconnection, where magnetic field lines can actually reconnect into a different type of magnetic field configuration. So that's one of the things that I'm working on. I'm also working on the region in front of the magnetic field, because the solar wind is traveling at, for example, the solar wind is traveling at a very fast speed, right? And we know from aerospace, right, that when you have a fighter jet, for example, going at supersonic speed, you form a shock in front, right? Or any supersonic flight, you form a shock in front. So it's the same thing for Earth, right? And so the solar wind comes in, it's traveling at a very fast speed, it forms what we call a bow shock in front of the Earth, and anything in front of that, right, is the solar wind. And how the solar wind interact with this bow shock is also another plasma physics area that I'm working on right now. And then I'm also working on Mercury. So I study the Mercury's magnetosphere and all the plasma phenomenon that is actually occurring in the in that mini, we call it a miniature. It sounds very cute, mini magnetosphere. but it's very highly dynamic also, and people has been talking about about the plasma phenomenon in there, and how are we going to send. Well, I mean, if you think that sending a rover to Mars is difficult, wait until you send a rover to Mercury, because it's a totally different ball game on the surface of Mercury. Okay, so that's the research that I'm working on now. Quite frankly speaking, there's a lot of people working on different areas of planetary science, heliophysics, space weather, everything. Down from the upper atmosphere of Earth, okay, all the way out to the edge of the solar system. Okay, and every single body that you can think of, the Earth, all the planets, right? Even up to people are sending spacecraft to Pluto. Pluto is not being left out right now. People are New Horizon is out so far out, near Pluto, to really study the plasma environment at Pluto itself. People looking at the sun, people looking at how the sun interacts with all the magnetosphere. Okay, people looking at the heliosphere, and then we are now actually expanding all the way out to the astrophysics people, because you have exoplanets, the hot Jupiters. They also have their own magnetic field. They are closer to their own sun, right? And they interact with their sun also. And how those the hot Jupiters keep their atmosphere, okay? Because they are so close, and their atmosphere is constantly also being stripped away by their own sun, okay? So these are the things that people work on, okay? Now, with that being said, there's a huge range of variety of research that people, so there's not really a specific things that people go towards, okay? But with that being said, NASA has different flight mission opportunities, right? And it goes in a kind of a cycle in that sense. Like, for example, certain years, NASA decided to put more emphasis on a particular planet, okay? And then once the mission is done, they will wait. Usually you have to wait until like a decade long, before the next mission to the same planet is being planned or even being considered. Okay, so for example, right now, the next thing that people are trying to do for research, right, of course, is lunar, right? The Artemis program. People are really trying to get. NASA and a lot of commercial space are trying to get people on the moon, and they're trying to get people on Mars also. So lunar and Mars is the next big thing. Now, for research wise, as far as I know, there's a lot of new missions that is going to be sent to Jupiter, particularly to study the moon, the Europa. I think there's a Europa mission that is going on right now. And really to study the Jovian moons and the Jovian plasma environment. Most recently, NASA is going to send 2 spacecraft to Venus, because Venus is long overdue. NASA hasn't sent a spacecraft to Venus for a very long time already. So they have 2 spacecraft going there. Now that's only NASA alone, right? European Space Agency has its own agenda. They are also sending I think, as far as I know, they are sending a lot of spacecraft to, some of the planetary bodies like comets, and things like that. For example, I believe Rosetta. Yeah, that's another one that was going on. I think it's still going on, but I might be wrong. But they have other missions. Like, for example, ESA is also going to have a mission very soon. That the spacecraft is going to reach Mercury actually in a couple of years' time. So that's also the next big thing that is going to happen. And then you have Solar Orbiter and the Parker Solar Probe. Those 2 spacecraft are going to really understand the sun, and how the sun gives out the solar wind, how space weather is. Space weather starts from the sun, right? So they really want to study the sun. So I can go on forever and forever. I mean, 1 minute left, but I can go on forever and forever. But I hope to kind of convey the message that it's really a very exciting time to be in heliophysics and planetary science right now. But I'm going to leave it there.
So the TLDR version, guys, is that there is endless opportunities for you to study anything you want out there. Yes, a lot of learning, a lot of ways that you can actually a lot of exciting areas that you can go into research if that's an area that you want to go into. Of course, the space industry isn't just research and science, and there's also like the business aspects of it, which you'll see a couple of lectures later on, or like a couple of seminars later on. We have one on financing for space missions and all that. But yeah, I think this is where we can kind of close off for today. Thank you to everyone who's been sticking around. But before you leave, we do have a couple of announcements. So as I mentioned, the webinars for the next 2 weeks, so next week we have a webinar specifically for the starter category participants, but everyone is welcome to join. It will be on experiments on the ISS. So this for starter category students or participants. This is a great opportunity for you to figure out or learn more about what are the possible experiments that you can send up to the space station to keep in there to study on board. And then the following week's webinar will be on the Van Allen belts by Ms. Ling Ying. So she will be sharing more, like a bit more about what Gang Kai has been sharing, Dr. Po has been sharing today. And actually not tied to the ISC webinar series, we do have a webinar coming up this Wednesday, Singapore time Wednesday, 9 a.m. GMT +8, with Dr. Franklin Cheng Diaz, who is a physicist and former NASA astronaut. He has 25 veteran years of experience with NASA, and he'll be discussing with Ms. Lynette Tan, the Chief Executive of SSTL, about clean energy and space innovation. So if this is something that we are doing this in collaboration with the Costa Rica Bicentennial Independence Day. So if this is something that interests you guys, we will share the link in the chat. And you guys can register for this webinar. It's open for all. It's not really tied to regards to space weather, but this is another area that you can look into if you are just curious. And it's exciting, right? Because how often do you get to hear from a former NASA astronaut? But yeah, so besides that, this is at, again, 15 September, 9 a.m. GMT +8. Dr. Franklin Cheng Diaz will be tuning in from, I believe, Costa Rica. I'm not sure where he's based currently. But yeah. And then our next 2 ISC webinars will be on Saturday at 11 a.m. GMT +8. So it's not going to be at night anymore if you guys are used to that. We're shifting things around just so that everyone gets a chance to attend regardless of their schedule. But yeah, besides that, I hope everyone has a good evening or morning, or for wherever you are, a good day. And I look forward to seeing you guys next week. So thank you all for your questions. I will send the questions that we didn't get to answer today to Dr. Po to answer through email, and then we can maybe share it in a post on the website, or send it through email to you guys as well, along with the recordings. I have not forgotten the recordings.